introductions. I love the Spanish language, so thank you. Um, and thank you all for being here. I'm really excited to share with you some of the work that we're doing on liquid metals. Are you able to hear okay? You're able to see and that's good?
Yes,
Okay, wonderful.
very clear.
So I thought I'd start with just a little introduction about where I'm from, because I'm quite sad that I couldn't come and see you all in person, and I hope that someday I can. But for now, we'll do this virtually. And so I'm a professor at NC State University, it's North Carolina State, and we are called the Wolf Pack. So you'll see in this slide, let's see if we can get the laser pointer. You can see the wolves, and there's we call this Mr. Wolf. This is part of our campus, and this is our, well, we call it football, but American football stadium. Our university is located in the middle of the state of North Carolina. So this is North Carolina, Atlantic coast. So we're on the East Coast, and Raleigh is the capital, and it's right in the middle of the state. So if you drive a few hours this way, you can go to the beach. And if you drive a few hours this way, we have really beautiful mountains. And because of this and a number of other reasons, Raleigh, where we live, is actually considered one of the best places to live in the whole country. So one thing I would like to do on Friday, if you'll come back, is to tell you a little bit more about opportunities for students. So if those of you that are undergraduates, if you are considering graduate school, I'd like to tell you about how that works, and tell you a little bit more about Raleigh and our department. This is actually our building. Sadly, I only go there about one day a month these days because of COVID. And this is our engineering library, which is a really beautiful building. We are one of the biggest schools in the state of North Carolina. I think we are the biggest school, about 33,000 people. So it's quite large. Okay, so this is my plan. Today, I'm hoping to tell you about liquid metals, which I think you'll find interesting. I've got a lot of fun videos. This is meant to be just really kind of fun for students, and talk a little bit about patterning liquid metals. So that'll make more sense in just a second. On Wednesday, I hope to tell you a little bit more about liquid metal. So liquid metal particles and interfaces. And then Friday, I'm going to talk about a different topic, talking about patterning of polymers. So 3D, going from 2D to 3D shapes. I think you'll also really enjoy that. So that's the plan. And the motivation for what I'm hoping to tell you about today is this. It looks a little bit like science fiction, but this idea that in the future, devices, whether they be electronics. So, I have here my cell phone, which is completely made out of hard materials, as well as robotics tend to be made out of rigid materials. Yet our bodies are made almost entirely out of soft materials, our brains, our muscles. And so there's this mechanical disconnect between these rigid devices and the human body. And so the thought is, if you can start making devices soft, you might be able to make them in a way that can interact with humans in a safe way. So here are some examples of electronics that are flexible, soft, and stretchable. So maybe I can start here. So this was a device that was envisioned by a company called Nokia, and they envisioned this would be like a cell phone that could wrap around your wrist like a watch, and then when you use it, it goes back to the flat state. This is some work from John Rogers. He's one of the leaders in this field, probably the leader in this field, and he has come up with this way to make very thin electronics that actually can be worn against the skin. And so this is very exciting for wearable devices. This is an example of an implantable device that was done by Stephanie Lacour in Europe in Switzerland. And the idea for this is to help people that have back injuries. so that if you implant this inside the body, because it's soft and stretchable, when you move around, it doesn't damage the surrounding tissue. Um, Maybe just focus on one more example here, and this is the human body, which I already talked about, but the human body is amazing in all the things that it can do. And I'm going to tell you a little bit of some examples of stuff that's inspired by the human body. So there's three words here: flexible, soft, and stretchable. So let me talk about flexible first. If you want to make something flexible, this is very easy to do, because if you can take a rigid material, like this is a piece of wood that's used for building houses, and you make it thin enough, you have something that's flexible. So I've got an example here. You can see this piece of paper can easily bend, no problem, but it's not stretchable and it's not soft. Same thing for this is aluminum. This is a bicycle made out of aluminum. And if you make it thin enough, then you have aluminum foil. But neither one of these is stretchable and neither one of these is soft. So, one way to make them stretchable is by taking these same materials. So, imagine you have a piece of metal that's very thin and you can bend it. So, I can take this and I can make it sort of stretchable just by bending it in and out of plane. And so, this is one approach that people have taken. Another approach is that if you want to make a stretchable conductor, is you can take conductive particles and put them into a stretchable material. So when you stretch it, the conductors maintain their conductive path, and this actually works quite well. But there is one sort of trade-off here, and that is as you take these conductive particles and you start putting them into the elastomer, first of all, you need to have a lot of particles so that they have a conductive path, so that the electricity can go through here. So to get your conductivity up, you have to add a lot of filler. And if you add, the more filler you add, you make the stretchability less and less. So this is sort of a trade-off with this composites approach. So there's a third approach, which is what I'm going to talk about, and that is to make materials that are intrinsically stretchable, like liquid metal. So if you have your conductor made out of liquid metal and you stretch it, you can make it longer without changing the conductivity. So why do we pick liquid metals? Because they're soft and they're stretchable. So this is the modulus of some common materials. So if you go way over here, you'll see diamond. This is very, very hard material. So 10 to the 12th pascals. If you go a million times softer, so go all the way over here, this is rubber. So this is, like this rubber band. So this is stretchy and quite soft. If you go 1,000 times softer, then you get into tissue, like your skin. And if you go all the way over here, you'll see liquid metals. And of course, liquid metals are interesting because they're metallically conductive. But there's sort of two problems. One is that usually when people think of liquid metal, they think of two things: either the movie, The Terminator, or mercury. And so I've got a little video clip here in case you haven't seen this movie. This is the former governor of California, who Arnold Schwarzenegger, who has just blown up the bad guy, and the bad guy turns into this liquid metal like material. And I actually had the good fortune of talking to the producer that made this movie, and he actually used mercury to do the computer graphics. So this movie, I think, came out in the early 1990s, maybe 1993. And this was the first really fantastic use of computers to do graphic rendering. So anyway, unfortunately, the bad thing is that people think of mercury, which is toxic, or the Terminator when they think of liquid metal. But I'm going to tell you, there's other options. And to really drive home this point, I just told you that if you use a composite to make a stretchable conductor, so you take a piece of rubber, and this thing is very, very stretchable. So on this axis, it's way over here, but it's not very conductive. So it's down, it would be like maybe here. So I can make it conductive by starting to put silver or carbon particles to make it more conductive. But when I do that, I make it less stretchable. So there's this general trade off with composites. With liquid metal, you can make it very stretchable and very conductive. So let's see if this works. So this is a rubber tube filled with liquid metal. And you'll hear some sound. So as you can hear from this video, there is no degradation in the volume or the sound quality. And we were able to get a wire that's stretchable, like a piece of rubber, but has electrical properties like metal. So this kind of gives you the best of both worlds. You get stretchable and conductive. Okay, now we still have one problem, which is how do we pick a liquid metal? And so, what most people think when they think of liquid metal is mercury. And mercury, of course, is toxic. So we want to avoid that. If you go way to the left side of the periodic table, there's these elements here that have low melting points. However, they are explosive and in some cases radioactive. So these are not good choices either. So the only thing that's left is gallium. And gallium is, in my opinion, one of the most interesting materials on the entire periodic table. You'll notice right away that it's below aluminum, which means that they are like brothers or sisters. They have very similar properties. And that's important. And I'll tell you why in a second. But there's one big difference, and that is that gallium has a low melting point. So about 30 degrees Celsius. So that means if you hold it in your hand, it would melt. So this is a crystal of gallium. And we want to make sure that it's liquid at room temperature. So to do that, we add other metals like indium. And so this is one of the interesting things about nature. When you mix together two materials, you end up with something that's got a lower melting point. And we choose the composition that gives us the lowest melting point, which is about 15 or 16 degrees. And so that's called the eutectic. And in this particular case, that's 75% gallium and 25% indium. And so we call it eutectic, gallium, and indium. So I will try not to say this word, but if you see this on the slides, you'll know that it's referring to eutectic, gallium, indium. Okay, so I mentioned many amazing properties. This is a video that shows that you can take the metal, squirt it out of a syringe. So it's a liquid. It's got metallic conductivity. If you swirl it around, you start to see some weird behavior. It takes on some shape that would normally not be associated with high surface tension liquids. And that's because the surface reacts with air and forms an oxide. If you dissolve away the oxide, the metal simply beads up, and due to its very high surface tension. So because of the very large surface tension of the metal, it tends to form a sphere. So the most important point from this slide is that it reacts with air and forms a very thin oxide layer. It's about 3 nanometers thick. And that has a big, profound effect on its behavior. And I'll show you in just a moment. Another interesting thing, it's got 0 vapor pressure. That means, so I have some water here. And water has a vapor pressure. So if I leave this cup here, it's going to eventually evaporate. This has no vapor pressure, so it will not evaporate. So you don't have to worry about breathing it. And people always say, well, oh, it's a liquid metal, so it's probably got high toxicity. And actually, no, it does not. Mercury is toxic, but not gallium. So one of my colleagues came up with this idea of using liquid metal for medicine. And so I thought that was a little bit crazy, but it turned out to be a good idea. And this is my former student and her husband, and they actually studied the toxicity of gallium and found it to not be toxic. So we still treat it very carefully, but it suggests that the toxicity is low. Now, gallium is not found in the body naturally, so it still should be something you handle with care. Okay, so I want to talk about this because this is very, very important, but it's not surprising. In fact, most metals react with air and form an oxide. So if you take aluminum foil, that actually has a very thin oxide on it, and they call it passivating because what it means is it forms and it stops. So it doesn't let more oxygen diffuse through and get to the metal. And this is actually very, very important because without oxides, there would be no metals. They would just react with air other than gold and platinum. And so what do we know about this oxide? Well, here is a picture of our liquid metal, and this is a side view. So you can see the oxide is a few nanometers thick. So it's very, very thin. And this is not new. In fact, this is a paper from 1954, and it was published in Science, believe it or not. And what these authors were trying to do was a technique called pyrography. This is where you take a needle and you pump liquid metal out, and you use that as an electrode for electrochemistry. And what they found, they said, despite all precautions, this gallium electrode always behaved erratically. So that means like it doesn't behave consistent, especially with regard to dropping rate. So how often they pump it out and it drops and drops and drops. So it says this could never be reproduced from one run to the other for a given applied pressure. And so this was actually a science paper. This is the most prestigious journal in the world, or one of the most, and it's reporting a failed experiment. So you would not see something like this these days. So there's a reason that this occurs, and I will show you on this next slide. So we wanted to understand why this is flowing in such a weird way. And so what we did is we put the liquid metal between two plates, and we can use my water here, and we turn the plate back and forth. This plate is about the size of a cookie, so it's about this big. And what we measure is the torque required to turn this back and forth. Now, normally this is a bulk measurement, which means we're measuring the entire material. But if you take a cutaway view, the liquid itself is like water. So it's got a viscosity, but it's so low that you really can't measure it. I mean, you can't measure it using this technique. So what you're really measuring is this solid skin. All right, so let me show you this video. So this is the liquid metal here. This is the top plate, and this is the bottom plate. So we tell it to go right, left, and then we let it go. So let me show you that one more time. You can see the oxide wrinkle, and then when we let it go, it's got a little bit of elasticity. It actually comes back. It's sort of like stretching a rubber band. So from these measurements, we get this information. This is the elastic modulus. Actually, it's the elastic surface modulus. So it's newtons per meter, and it's plotted as a function of surface stress. So if you think about the stress like this, when you try to stretch something, oops, it broke. When you stretch something, there is, at least in the case of a piece of rubber, there's the modulus, or you might think of it like a spring constant, like Hooke's law. And that constant is what's being plotted right here. And what this shows is that that oxide skin is elastic until you reach a critical stress. So right around here, you see that it drops. And what happens there is the oxide actually breaks. So this is like a very important point. So if you are above this stress, the oxide will break and the metal will flow. If you're below this stress, it will not. And so ketchup is sort of the same way. If you take ketchup and you hold it upside down and squeeze it, nothing happens, and then suddenly it squirts out. Well, this is very, very similar, but a different physical mechanism, but similar behavior. So we actually went in with my colleague, Professor Shao, and she her and her student, we looked at gallium. So this is just pure gallium, gallium indium, and then this is called gallium-STAN. This is gallium indium tin. And you'll see that all of them are exactly the same. And so what that means is that even though you change the composition of the liquid metal by adding indium, for example, it's really gallium oxide that dominates the properties. Okay, so that means everything I'm going to show you would work for gallium, gallium indium tin. It doesn't matter. As long as it has gallium, it's going to be gallium oxide. Okay, so why am I making a big deal about this oxide layer? Well, one of the things that's really exciting is that it allows you to pattern the metal. So this video shows a syringe where we're dispensing a droplet, and here we're actually pulling the droplet back in. You can see the oxide wrinkle. And this oxide forms so fast and is so strong that you can actually start printing this liquid metal at room temperature. So you can start making shapes. And this is the first time, and I think the only way that I know of, that you can print liquids at room temperature. So here we're stacking droplets, and that 3 nanometer oxide layer is holding this whole thing together. Now you can also do a burst of pressure, and it will shoot out of the nozzle, and it oxidizes so fast that it forms a fiber. So you can drag it around like a hose and make electrical connections. And then this is a dead bug. So these are the eyes. And the bug was already dead, so don't worry. And so this really shows how gentle this printing process is. It's truly room temperature, and these structures are on the order of 100 microns or so. They're about the size of a human hair. So they're quite small. So we can 3D print it. You can also direct print it. So this is a needle with the liquid metal, and we just basically are dragging it across the surface. This works very much the same way as a pen, where when you drag it across the surface, the liquid comes out. Again, this is at room temperature. There's no tricks. This is real time. It's very, very simple to do. Okay, so now we can start making metals that are liquids into interesting structures. So that's one way we can pattern it. Another way you can pattern it is simply to stretch it. So here we put it on some putty, some polymer. And when you stretch it, you can make the wire longer. And these types of wires are interesting because they're really good conductors, and you can actually use them for a number of things. So for example, here we use, these are actually 3 fibers that are twisted together, and we fill them with different lengths of metal. And we use the capacitance between your finger, or between a finger and the wire, to detect touch. So this is very similar to your smartphone, your screen on your phone. But here we're doing it in a fiber form factor that's completely stretchable. Okay, so another way we can pattern the metal is to inject it. So this is a microfluidic channel. There's a hole here, and there's a tube that goes all the way to right here. So we apply some pressure. That pressure breaks the oxide, and the metal flows in because of its low viscosity. So remember, it's like water. It flows in, but then it holds its shape because it reforms that oxide layer. And so we've used this to form, these are different wires. This is actually an antenna. This is also an antenna that's used for wireless power transfer. These are electrodes that are in microfluidic channels for applying electric fields or doing electrochemistry. Okay, so there's a bunch of different applications of this, but it turns out it's even easier to pattern the metal using a technique that's called vacuum filling. So I need to explain this. Actually, maybe I'll go back here. So in the previous video, there was an inlet hole and an outlet hole. So if you imagine this is your channel, you inject the metal here, and the air comes out here, so it flows in. And this video, maybe you can see, but there's some channels, some very small tubes, and there's only one inlet. So there's an inlet, but no outlet. And over that inlet, we place the liquid metal. In fact, If you look carefully, you'll see my student. You can see his reflection right here. We put that whole thing in a vacuum, in a chamber, and we pull all the air out. Well, when you do that, you remove the air from these channels because the air can diffuse through this. This is a silicone. So the student is going to come. If you watch right here, he's going to come and turn the valve, which is going to let air back into the channel. And that's going to apply pressure right here. So now atmospheric pressure is pushing, and that pushes it into the channels because the channels remain under vacuum. So this is a really simple way to pattern the metal in it with no hands. You just use pressure differentials. Okay. So these are some ways to pattern the metal, but there's some problems. And one problem is that these silicone materials that are very popular don't have very good mechanical properties. In fact, if you take these silicones, you can very easily tear them if you would like. So I'm going to tell you 3 approaches that we have looked at to address this issue. So the first one is, okay, well, what if we just don't use silicone? What if we use a different material? So here is a very special polymer that has liquid metal inside, and there's electricity going through this wire that lights up this LED. We then take scissors and we cut it. And when you cut it, you break the circuit electrically, so you see the light has turned off, and you break it mechanically. Now, the key thing, if you notice at this interface, there's no liquid coming out, and that's because the oxide forms so fast. So when you bring it back together, that wire will heal electrically. And then what's also special is this polymer is actually held together by hydrogen bonds. So normally when you cut a material, you can't put it back together. But this one, when you put it back together, those hydrogen bonds move around and find each other. And so when you pull on it, it's now healed mechanically and electrically. And so anyway, so this is one approach to kind of making a better material. Another approach is to try to make a tougher material. And a tough material is one that dissipates energy, that can absorb a lot of energy. And so this is kind of the key idea. You need a material that is elastic. And so again, I have a rubber band here. So this is elastic, but it's not tough because it doesn't dissipate energy. So you also need some energy dissipating mechanism. So let me give you sort of an analogy. So this person here is exercising, and he is kind of funny. He's attached himself to a rubber band. So this is an example of an elastic system, but it's not dissipating energy. Now, if this same person was running through water and attached to a piece of rubber, then that would be energy dissipating and elastic. You can also dissipate energy by breaking materials, and that's what I'm going to show you in just a second. Okay, so here's the basic idea. If you take a piece of rubber, again, like this one here, and you stretch it, you will get a stress, which is basically, this is like the force versus strain that's very low, but it can go to very high strains. And the area under here is the energy dissipated, because energy is force times distance. So this is force, this is distance, this area is the toughness. Or you could take something like, a piece of metal and pull on it, and it would require a very large stress, but it would break. So again, the area underneath here is the toughness. So neither one of these materials is actually very tough. But what if we could combine the two? In other words, get something that goes to high stress, but also goes to high strain. Then the area under here, we would get something that's very tough. So the way that we do this is we put the liquid metal inside of a rubber tube and then we freeze it. So instead of it being a liquid, it's actually solid. And when you pull on it, it will break. But instead of breaking and falling apart, it will be held together by the polymer. The polymer will sort of hold the wire together. And so then it will stretch again and it will break and stretch and break. And if you can do this multiple times, you can get a very tough material. So here is a video. This is one of these fibers, and this has solid, so it's not liquid, solid gallium. And when we stretch it, you'll see that initially we actually will stretch the metal. And if you watch maybe here, you'll see, oh, there it goes. It breaks, and then it breaks again, and it breaks again, and it breaks again. And it keeps going to very high strains. And if you go far enough, eventually it will completely break. And so if you plot the stress versus strain, so again, this is stress, this is strain, you'll see that initially the stress goes straight up. That means it's very stiff. And then the metal starts to lengthen, and then it breaks. And then it stretches some more and it breaks again, and it breaks again. And so every time it breaks, it's helping to dissipate energy. And so this is not a perfect analogy, but imagine if you get in like an accident and someone hits you on your arm. Well, if your arm breaks, if you break your bone, your arm does not fall off. And I know that sounds silly, but the point is that the skin, which is elastic, helps hold this together. And so imagine basically what we're doing here is breaking the bone multiple times. And so we end up with a material that's 4 times tougher than skin and 2.5 times tougher than this. This is a protein that helps toughen muscles. So here's a demonstration. So over here, we have a weight, a piece of metal that's hanging from this rubber tube. So this one is just elastic, just rubber. Over here, we have a fiber that's got the elastic part, but also has an energy dissipated mechanism. So if you watch, here we go. We're going to drop, and you see that the elastic one just falls right away, whereas this one dissipates energy as it falls. So, for a stretchable device, you actually want properties that are actually a little bit different, that actually are more like skin. And this guy is kind of strange looking. But skin, as you know, is a little bit stretchable, but then it gets very stiff. And so they call this a J-shape behavior, J-shape, because when you start straining your skin, and you can think about your skin like this, it's very easy to strain it. And then at some point it becomes very difficult. And this is actually ideal for some stretchable device. You want it to be very easy to stretch, but not too far so it doesn't break. And so we can actually do this. So when we make our first stretch, it's actually stiff. So this is not good. But then it breaks, and then it breaks again. So then if we take the thing and we stretch it a second time, because we already have these breaks, the second time it will actually look like a J, this orange data. It will be very easy to stretch, and then it gets much, much stiffer. Okay, so just for fun, I'm going to tell you a little bit more about sort of skin and the body as inspiration. Okay, let's see. My computer's, there we go, it's acting a little funny. So I talked about skin, but there's also muscle, which is another very interesting and tough material. But muscle, as you know, it can go from being very kind of, very soft to being quite stiff. And so we've used these same fibers to tune the rigidity of these stretchy material. So this is our elastomer tube, and we put in liquid gallium, which is soft. So it's soft and stretchy. And then we can freeze it. We can freeze the wire, and that can cause it to be stiff. And so this allows us to do some kind of interesting things. So these are some fibers that we froze the gallium, and you can see it will kind of keep its shape. So you can make it into whatever shape you want, but it's still metallically conductive. So you can see the resistance is very, very low. And when you put it into warm water, it will melt. And when it melts, it goes back completely back to the soft state. So you can get, I think it's like 1,000 times change in the modulus just by controlling the temperature. So we use this for what's called shape memory. And the idea here is that you take a fiber and you stretch it. And once you stretch it, you freeze it. And so when it's frozen, you can then let it go. So this bottom part, so you pull on it and then you let it go, and you measure what's called the fixity. That's how much of its original stretch length does it keep when you let it go. Because normally if you stretch something and you let it go, it goes back to its original length. But here we get about 100% fixity to very large strains. Then you take that and you heat it. And when you heat it, my computer is not happy at the moment. I think I'm going to try something. Okay, so when you heat it, it will, the core melts and it will go from its stretch state back to its original length. And so that's called recovery. And you can see these fibers also have amazing recovery. Okay, so I told you I was going to give you 3 approaches to dealing with silicones. And there's a third approach, and this is the third and final approach, which is to actually use the silicone. So this is a piece of silicone. And remember, silicones, if you pull hard enough, you can break them. And so what we did in collaboration with this really good student named Meredith Barbie, we integrated this molecule that is called a spiropyrin. And that molecule is actually integrated directly into the silicone network, into the PDMS silicone. And when you pull on it, if you look at this molecule, and I know some of you are not chemists, so don't worry, but when you look at this molecule, it's got some rings structures. Well, think about what happens to a ring when you pull on it. It will have some stress, and then eventually it breaks. And the same thing happens here. But when this thing breaks, it actually turns purple. So we have a liquid metal wire in here, and we're going to stretch it, and you'll see that right before it's about to break, these molecules that are in the polymer get stressed and they change color. And so it tells you if this thing is about to break. So those rings open, and when you let it come back, the rings close and it goes back to being transparent. So what this does is it allows you to know before this material is going to break, which is very nice. Okay, so this actually got us thinking a little bit about color. And so if you think about color, being able to control color in soft materials, in our daily lives, we use color for expression. For example, if you're embarrassed, maybe your skin turns a little bit red. And nature uses this for camouflage and for other survival instincts. And then we also use it in our daily lives for looking at screens, looking at our phones. And so, so basically the idea is, can we control color in a soft material? So I'm going to show you 2 examples, I think. The first one is very simple. And so this was a device that we made a long time ago. And one thing that was very weird was that you see there's some color. It looks like it's some reason the liquid metal is colorful. And so this caused us to do a kind of a curiosity-driven research where we took the liquid metal. So remember, this is eutectic gallium and indium, and we put it into a microchannel, so very small channel, and then we squeezed it. And so when you squeeze it, just using a little bit of pressure, we found that we could see some color. And so that was very, very weird. So, but turns out that what's happening here is actually quite simple. So if you have a flat surface and light comes down and hits that surface, it bounces off like a mirror. However, when you squeeze something and you squeeze something that's rigid, like that oxide layer, it's going to form little buckles, just like it's happening here in my hand. And so when we did this, basically when you squeeze these things, you form little corrugations. And those corrugations act like diffraction gratings that will cause the light to diffract, and therefore it appears colorful. So this is kind of cool because we're able to get color from structure, from shape, not from a dye. But there are other approaches to changing color? And the answer is yes. Otherwise, I wouldn't have said this. And so what we did was we took liquid metal and we injected it into silicone, and that silicone had a special pigment in it that looks blue. When you heat up this pigment, the color changes to white because there's a change in the pigment due to temperature. And so these are called thermochromic. So thermo meaning heat, temperature, and chromic meaning color. So it's soft because it's made out of liquid metal. It changes temperature because of electricity, and it's chromic meaning it changes color. So we can do this with a blue pigment. We can also do it with a red pigment. So here we made a little pattern, and you can see this is the IR camera image on the left. You can see that it gets warm wherever we apply the electricity. All right, so so it turns out that the red and the blue have different temperatures where they change color. And so we can combine the red and the blue, and we get purple. And so if you apply a little bit of current, you can make the red disappear, and so it appears blue. And if you apply more current, you can get the blue to disappear. Now it appears white. So this is simply taking it to different temperatures. And now if you let it cool back down, those colors will come back. Okay, so the basic idea is we're using temperature to cause a change in color. Well, everything I've shown you doesn't really require liquid metal. But where this gets interesting is if you run electricity, so here's some wires. So we run electricity through this polymer and it comes out the other side. If we apply pressure, we can actually take the liquid metal and squeeze it and change the resistance. And when we do that, let's see, oops. When we do that, we increase the resistance right here. So when you apply a little bit of pressure, you can start seeing color change. So now we apply more pressure and we see more color change and more pressure. Okay, so now we have a way to make this material responsive to touch. But it actually is a little bit even more interesting. So this is the same material. It's purple. It's a little bit difficult to see, but there's a liquid metal wire, a single wire that goes straight through this material. And we run constant current, and the current is not enough to cause color change. So you'll see that initially it's purple. Then when we start stretching it, we're going to make that wire longer, just like this rubber band. You make it longer. And when you make it longer and narrower, the resistance goes up. And so you start seeing color as a result of mechanical stress. And so this is interesting because it basically couples mechanical effects with electrical effects and optical. Okay, so that's kind of cool. But I would like to tell you why I think that this is the most interesting. And I need to tell you a little bit of motivation. So right here, I have my cell phone. And if I want to grab it, usually what I do is I look with my eyes and I come and touch it. And then I squeeze it with the right amount of force and and then I can hold it, no problem. So it's this idea that you first will sense something with your skin or your eyes. That sends a signal to your brain, and your brain tells your hand what to do. So sense, compute, respond. Now, if you wanted to make a robot to do this, you would have a sensor like a camera, a computer that can handle this information, and then a motor that would tell the robot what to do. But the problem is that in your arm, just in a human arm, there's like a million sensing nerves, which is just crazy. So if you try to do this with a robot, this is hopefully you all have seen Star Wars. This is C-3PO, and his arm got torn off, and you can see there's all these wires. So if you tried to make a centralized brain in a robot and a million wires that come through here, this becomes very, very difficult. And so very complex. So the idea is, well, okay, what if we could actually have the sensing and the responding happen without the brain? In other words, when your skin or the robot touches something, it knows exactly what to do based on those sensory inputs. And so this sounds crazy, except if you think about Mother Nature, there's an octopus has actually about 2/3 of its neurons are in its arms. So in a human, invertebrates, the brain is typically centralized inside of a protective skull. But in these octopus, which are just these amazing creatures, they have neurons in their arms, which then raises a lot of interesting questions like how are they controlling their arms and these kinds of things. So this is sometimes called distributed logic. So instead of having it in a central place, you have it kind of distributed. Okay, so we cannot do this, but we have a very modest step in this direction. So we made a very simple circuit that has A, B, and C. And the current goes through A, B, and C. So if you flip this over, this is region C, and you can see that it looks purple. However, if we come and push in region A, we're going to redirect the electricity so that there's now more electricity here. And so now we get a blue color because it's warm enough that the red disappears. If we push A and B, we're squishing the liquid metal and we're redirecting the current to a different position. So you'll notice that these changes are occurring. There's no computer chip. All we're doing is touching the material, and based on how we touch it, we get a output that depends on the way that you touch it. If you touch it here or together. And as we did this work, I started reading a lot about Mother Nature, and it turns out that the Venus flytrap, these plants actually grow in North Carolina. So these are these plants that will close. And one of the problems is if they were just to simply close when they get one touch, they would waste a lot of energy because sometimes there's not even a bug, an insect that's touched it. So it actually requires 2 or more points of contact. So if this is your Venus flytrap, it has to kind of touch multiple times and then it will close. So again, we can't do this, but it's sort of gets you thinking about, materials, very simple materials that can somehow respond appropriately depending on the way they're touched. So in the example that I showed, we use color, but you can actually use the electricity to do other things. So for example, in this example, we have liquid metal wires that are in these tubes. So one is labeled A, one is labeled B, and the student created this really clever circuit that has a motor. This is a DC motor and an LED, which is a little hard to see. So when we start, you'll see there's nothing turned on. If you squeeze A, then the motor turns on. If you squeeze A and B, then you see the LED comes on. And so depending on the combination of how you touch this, you can get multiple states. And all that's happening here is we're just redirecting electricity to different parts of this circuit. Okay, so while we're talking about this kind of tactile touch, response to touch, skin is again just this amazing material that we really take for granted, and it's capable of measuring temperature. It's capable of healing. It's capable of doing a lot of things. But one of the things it's capable of doing is detecting very sensitive touch, and also with large dynamic range, which means it can some barely touching or like really a lot of pressure. So one way people have measured touch is by using capacitive sensing. And so the idea is that if you have two parallel plates separated by a gap and you push them, you will change the gap. And in some cases, if you push enough, you'll also increase the area. And so when you do this, if you can measure the change in capacitance, delta C, it will increase because of changes in the distance between those capacitor plates. So if you want to make this thing really sensitive, what you want to have is a low modulus, so that's very easy to press this. You want to increase the dielectric constant. This is kind of a challenge because most soft materials have very low dielectric constant. And then you want to, if one thing would be really cool but difficult to do, is to make the dielectric a function of D. So as you squeeze it, the dielectric would increase or decrease. So one trick that people have done is to make these things kind of soft. And one way to do it is if you, instead of having a big slab of polymer, so, again, I've got this rubber band here. It's very stretchy and soft, but if I try to squeeze it, it's kind of difficult to do. And so if you make it look like these pyramids, it actually becomes easier to squeeze. Another trick that people have done is increase the dielectric by putting liquid metal into the silicone. And that increases the dielectric constant. So if I go back, it increases this dielectric. And so that helps make it more sensitive. So we kind of did both of those things. So we mixed liquid metal with sugar and silicone. It's called EcoFlex. It's just a silicone. So we mix it together and then we dissolve out the sugar and we get this porous material. So I noticed someone raised their hand. I don't know if they had a question. And I've also not been paying attention to the chat. I'm sorry. If there's a question, feel free to speak up. I'm also happy to take questions at the end. For some reason, I'm not seeing the chat. I'm not sure.
Yeah, up to now, there is no questions.
Okay, all right, perfect. Okay, so we have this material, and this shows you kind of what it looks like. It's very soft and stretchy, like a sponge, and you can twist it, and there's liquid metal inside of it, but it's not leaking because it's completely encased in silicone. And so when you squeeze this, it's quite soft. In fact, if you measure the stress versus strain, it doesn't require very much at all until you push all the air out, at which point the stress goes way up. So this is another example of a J-shaped curve. Okay, so we wanted to see if this works. And again, here is our foam. We push on it and we measure the capacitance when we press this foam back and forth. So here's the capacitance plotted as a function of stress. So that's how hard we push on the material. And we see that the capacitance goes up. Now there's a family of curves here, and this represents no liquid metal. So you can see down here, the signal is very low. And then this is 40% liquid metal, which gives us very good signal. So what we've effectively done is increased the dielectric constant and made it a really good sensor. And so I need to mention a term that when I was a student, I didn't understand, and it's very simple, even though I didn't understand it. And that term, let's see, I think my computer's lagging here. Let's go back. So that term is called piezo. So piezo is a Greek word that means to squeeze. And there's different terms like piezoelectric, which means change in potential when you squeeze a material. Piezoresistive means change in resistance as you squeeze a material. And I'm going to show you a term that we sort of made up, but it's called piezopermittivity. And that's the change in the dielectric constant. So we went back and we measured the dielectric constant of these squishy foams that have liquid metal in them. And again, these squares, this is 0% liquid metal, 10%, 20, 30, and 40%. So you'll see at 0 strain that adding the liquid metal takes the dielectric from almost like 1, that's like air, that's nothing, and it makes it about 6. So that's a big improvement. But the other thing is the dielectric increases. And the reason it increases is that we are squeezing a foam. So we're replacing the air with material, actual material. But where this got really interesting, and I'm curious to like study this more, is at some point we actually see it go down. And I think, and I might be wrong, but I think this is the only report ever of a negative piezopermittivity. In other words, the dielectric gets lower. And I think this has to do with the fact that the liquid metal particles can actually change their geometry when you squish them. Okay, so in the end, what we found was that if you look at the permittivity of the material, so down here is silicone. Well, let me start over here. These are commercial silicones. So this is their modulus. This is sort of how stiff they are. If you make a silicone into a foam, you lower the modulus, but it's got a very low dielectric constant. So by adding the liquid metal, we were able to make the dielectric much higher. So this is also quite exciting. So speaking of piezo properties, I was really lucky to be part of this collaboration that discovered something that I think is pretty exciting. So in the previous work, we mixed liquid metal with liquid metal with silicone. But here we are mixing it with also with solid magnetic powder. So this is what it looks like. If you look under a microscope, it looks kind of like a mess. It's got these liquid metal particles, iron particles. And if you look at the elemental composition, you can see the iron and the gallium, they're all kind of all mixed together. And I need to tell you something about composites like these. So normally with conductive composites, for example, if you take silver flakes, like little pieces of silver, and you mix it with rubber, they're typically not conductive at all. However, there's a few groups that have come up with some very clever solutions by adding just the right mixture of stuff. You can make these things conductive. So this is what the silver ink looks like, and you can see it's stretchable. But one of the problems is that if you measure the conductivity, you see it actually gets lower. So that means the resistance is going way up. And so that's kind of a problem if you want to have a stretchable circuit. And the reason that's the case is that if you have particles, again, this might be silver, and you stretch them, you pull them further apart. So it's more difficult for the electricity to go through the material. In our case, because we have solid particles and liquid particles, when you stretch them, you actually can stretch the liquid metal particle, and you can maintain percolation, which just means there's a path for electrons. But what was really weird, and honestly, we don't understand this fully, but if you measure the resistivity as a function of strain, you get an enormous changes in resistance. So this means the material is getting more conductive, but look at the axis here. This is a log scale. So it goes from like 100 to 10 to 1 to 0.1. And that's only with 0.1 strain. So if I take this and stretch it like that, that's a strain of 1. 0.1 would be like this. You almost can't even see it. So with a very little strain, we're getting a huge change in conductivity. And so this, of course, is useful for making wearable sensors. So you'll notice this axis is actually a log axis. So what this means is if you bend your finger like this, you get 2 orders of magnitude change in resistance. So that's kind of exciting. All right, so what I've kind of shown you here are these composites where you mix liquid metal in with silicone. And more recently, we've been trying to print these things. So we call them liquid metal elastomer composites because the liquid metal is mixed with the silicone. So I'm going to show you kind of what this
Michael?
looks like. So these are 3 different nozzles that have different loadings of liquid metal. And so let's see if my computer will play here. So here it comes. Okay, so the one on the left is 30 weight percent. And you can see that it's kind of runny, kind of just flows. The middle one flows a little bit. And then the one on the right, which has 80 weight percent, it's a little bit frozen here. Let's see if it's going to play. I'm sorry, the video is kind of not playing smoothly, but you can see that it sort of holds its shape. And so what we want, when you want to print some of these inks, what you want to look for is a couple things. One is you want to look at the viscosity as a function of shear rate. So when you push an ink through a nozzle, you get high shear rates. And so you want something that actually gets easier to flow as you push it. So this is called shear thinning. And you can see that this black data, which is just the silicone, it's constant with respect to shear. So shear is like this. It's how you it's basically applying a shear stress to the material. Now, if we load it with a lot of liquid metal, 90 weight percent, you can see the viscosity goes up, but when we start pumping it, it goes down by orders of magnitude. So what this means is when you're pumping it, it will flow, but when you stop, it will hold its shape. We also look at the modulus of the material and try to figure out where we can form a gel-like material. Well, without going into a lot of details, the bottom line is that it works. And the video is not playing.
Well, yeah, Michael, there is one question.
Great.
A couple of questions from Jose del Carmen. I will give him a chance to.
Hello, what's up?
Hi, thank you for the question.
Thank you so much. Now, I am engineer and electronic. I have a question. What happened when the current limit is exceeded in this weird? What happened with the materials? Blow up, change the form, burn. I don't know. What happened?
So you mean if you run a lot of current through it? Is that sort of the question? So if you,
Yes.
yeah, okay, yeah. So there's, I guess, 3 parts to this answer. The first is if you take one of these wires, which remember they're about the size of a human hair, so they're very small. If you run, in our experience, you can run literally amps of current through it without any problem. And so the short answer is nothing happens. It's kind of boring. But obviously, if you run enough current through it, they will start to get warm and you can get joule heating. They're not going to get really hot. They might, and in the experiments I've shown you, they go up to maybe 40 degrees Celsius or something. So it's, not enough to burn you, but that requires a lot of current. Now there is one more thing, which is there's an effect that's called electromigration, which means if you have a wire and electricity is going through it like this, you actually, the electrons are actually hitting the atoms and can push them in a direction. And so some people have shown that if you run enough current for a long enough time, the wires will eventually break. But they don't explode or anything. They just become not conductive. We almost never see that. So I think that's really requires a lot of current for a lot of time, but I don't have a good number off the top of my head just because we don't really see it. So, but it's a great question. Thank you.
Thank you so much.
Thank you. All right. So we have these materials now that, remember, these are liquid metal particles that are mixed with silicone. And because we've identified the right conditions to allow these to print, we can actually print them. And then we heat them up and that will cure the silicone. So it makes it stretchy. Like here it's a liquid, but once you heat it, it becomes stretchy. Okay. So yeah, these are just pictures of these wires. So maybe I'll skip over this, but they become conductive if you kind of squish them. Okay, so I'm impressed. I'm actually right on time. So just to kind of wrap up, what I've hopefully I've gotten you excited about liquid metals. That was my main goal, and to show you their unique properties, the fact that they are liquids but also metals. And a lot of what we've done is taking advantage of the native oxide, the very thin skin that forms on the surface. So this leads to things like stretchable wires, soft sensors, 3D printing that just simply aren't possible with other materials. I'd like to bring my outline back up just to remind you. So today I viewed this as like an introduction to talk about patterning and some of the neat applications that liquid metals enable. On Wednesday, I hope it's okay, but I'd like to talk about the particles of liquid metals and also the interfacial behavior, some really interesting stuff that we've observed and other people have observed. And then Friday, we'll change topics and talk about patterning of polymers. So I'd like to thank the students and people in my lab that have made this possible. I don't think I did any of the experiments that I showed you. So, all the credit goes to the really great students that we have. And I love to collaborate with people. So these are some names of people that I've worked with, and some of the work I showed. I tried to point out people's names as we went, but in case I missed them, I will mention them here. And these are the folks who've helped pay the bills the last few years and have been very supportive. And then I'll close with this slide, which is just, a couple of review articles. Not very active on Twitter, but we do have a Twitter site. And, we have some videos that are on YouTube, one of which is a TEDx talk that I think sort of highlights some of the stuff that I showed. So I hope that this is helpful, especially for the students. And I guess we have a break, but I'm very happy to take more questions. I tried to leave time for questions.
Yeah, many thanks, Michael. Very interesting talk and applications. There is one question from Alberto Beltran.
Hi, hello. This is Alberto Beltran from UNA.
Thank you.
Very nice your presentation. Thank you very much.
Thank you.
I was wondering, have you ever tried to study the effect of the stretching properties of this wire in the presence of a magnetic field? For instance, the one generated by permanent magnets. I'm wondering because if you start motion in the presence of a magnetic field, you might have an induced currents on the wire. So probably these induced currents will increase the stretching properties. I don't know. Have you ever tried to do that?
Yes and no. I love that idea. That's really clever. Yeah, we should try that. So the reason I said yes is because we have a collaboration where our collaborators are sort of doing that. And what's interesting is if you have a magnetic field that goes this way and you have electricity that goes this way, you get what's called a Lorentz force,
Right.
which can actually deflect the material. And it's difficult for me to answer this because I'm going to explain it on Wednesday, what we're doing.
Okay.
And so it might make more sense then, but we've actually been able to make liquid metal wires and get them to move in response to the magnetic field. But what we haven't done is to take like one of the stretchy wires and then put that in the magnetic field. And that's really cool. That's really clever.
Yes, even if you don't have a current, in principle, you should have induced currents on the liquid metal.
Yeah,
so
that's true too.
They will be very small, but I think that due to the high conductivity, there should be a small Lorentz force in the inside. So it might be interesting.
If you wouldn't mind, would you email me and then we can have one of my students try it and
Yes, of course.
send you the results.
Great, thank you.
Yeah, sure.
I will send you one of our publications too. Thank you.
Okay, yeah, that'd be great.
Okay, there is another question from Robin Rojas. Please.
Hello.
Hi.
Hi.
Hi, Robin.
It's a pleasure. I have a little doubt.
Thank you.
What happens if you expose you show us printed of gallium and indium, and you put a little pulse, one and one. And what happens if you put a magnetic field in that printed? The form can change, anything like that?
Yeah,
Yes.
so I think you're referring to this video. Well, gallium by itself is actually, I think they called diamagnetic, which means it doesn't really respond to magnets. Now, as Alberto said, if you run a current or you have things that are moving, that's a different story. But if you just simply use a magnet, nothing will happen because it doesn't respond. Now, that said, one of the cool things is that it's very easy to get magnetic particles to go into the metal. And other groups have done that. Not our group. Well, we've done some, we haven't published it. But if you do that, then you can actually get the metal to respond. So you have the liquid metal and you have little magnetic particles inside. And so we haven't tried to use that during the printing, but it's a really interesting idea. Man, another really great idea. That would be really fun to try as well. So thank you. You obviously had your coffee this morning.
Thank you.
Thanks. That's a great idea.
Okay, there is another question from Sergio Cuevas. Dr. Sergio Cuevas. Well, he wrote the question.
Okay.
He asked if there is a good rheological model to describe the liquid metal behavior.
Well, those are good questions. That's a good question. And there's two different things that I showed. There's the liquid metal itself, which I think is just this slide. And in this case, it's sort of simple in the sense that basically nothing happens and when I say nothing happens, I mean the metal does not flow until this yield stress is exceeded. And so what we have found is that we generally treat this oxide layer sort of like surface tension, in the sense that if you have a droplet of liquid and you try to make it bigger, you're going to be opposed by surface tension, which is like a membrane on the outside of of a liquid. And so we've generally found that in terms of like the pressure response of this material, that you could just treat it like Laplace pressure, which is just to say it's very much like surface tension. The difference, I'm a little reluctant to say that because that's only true in tension when you're trying to expand the droplet. When you try to recede it, it's a different story. So I guess to answer your question, it's sort of like a yield stress type fluid where nothing happens. You push, and then when it gets to a big enough stress, then it will flow. The other thing I showed was the liquid metal particles mixed with silicone. And with those, we use what's called a Herschel-Buckley model, which I think is used for quantifying the shear thinning behavior of materials that behave that way. And I'm by no means an expert on that, but that's what our rheologist friends suggested, and it actually fit the data pretty well. So I hope that answers it.
Okay, thanks. There is some questions in YouTube. One is asking about if you have studied the electrochemical properties of liquid metals.
Oh, that's a great question. You'll have to come back on Wednesday.
Okay.
The answer is yes, and it's absolutely fascinating. So, well, I don't want to spoil it too much, but we've been able to use electrochemical reactions to control the surface tension of the metal and to cause the biggest changes in surface tension ever reported using like 1 volt. And so we've been able to use that to control the shape of the metal. And you'll see it's to me, it's mind blowing. It's so hard to believe that it works.
Okay. We have to wait until Wednesday.
So yeah, the short answer is yes. And yeah, so you can use electrochemistry to remove the oxide layer, for example.
Okay, there is one question from Mohammed.
Here. I do have a question. Greeting Dr. Mickey, Dr. Michael Dickey. I have one question about how you mix the gallium with the indium. Have you tried mixing other kind of metals, like other kind of metal like indium or different type, or like nanoparticles of metals?
Yeah.
Yeah.
Good question. So the answer is yes. For the gallium and the indium, it's actually commercially available. So we don't actually mix them, but I believe it's pretty easy to do. So we just buy gallium indium. We don't even mix it. So I probably said we mix it, but I just meant it sort of figuratively. But your question is still a good one, and that is that I'll talk about this a little bit on Wednesday, but liquid metals tend to not want to wet any surface. So like if you took a droplet and put it on your hand, it would be like almost a perfect sphere. The only materials that it really wets, in my experience, is other metals. And it will do so, it can do so quite aggressively. And in the case of like aluminum, it's actually destructive. It will actually weaken aluminum. So this is one of the downsides of liquid metals, not just gallium, but other liquid metals, is that they can diffuse into other metals. But the flip side of that is people have used that to their advantage to mix liquid or solid particles into the liquid metal. Now, I mentioned that, and I'll tell you just kind of a funny story, which is we tried a long time ago, we tried to mix copper or silver, I don't remember, into gallium. And if you look at the phase diagram, they should absolutely want to mix, no problem. But we had a really difficult time. And I think that the issue is that because metals form these oxide layers, when you bring them, say, liquid metal and a solid metal together, the metal is actually not touching. And so the only way we really got them to mix is if we removed the oxide and made sure the particles were very clean. But if you do that, it will go in very easily, it's spontaneous. And I'll show you some examples of that on Wednesday. In fact, Yeah, I might even add a couple things to my slides based on that question, because I think it's kind of interesting to see. Yeah, thank you for the question. I don't know if I answered it to your liking, but hopefully the short answer is yes, you can do that. And we've done a little bit. And I'll try to show it on Wednesday.
Okay,
Thank you so much.
We have time for a couple of questions. There is one in YouTube, and Karen Sarmiento is asking about the types of sensors that has been evaluated using liquid metals.
That's a good question, and I don't know if I know all of them, but the ones off the top of my head. So the very simplest one is just taking a wire, and when you stretch it, you change the resistance because you change the geometry. So that would be considered a strain sensor. Likewise, if you push on the wire, you squish it, and that changes the resistance. So people have measured it for touch. People have measured it for strain and compression. And I showed a few examples today where we've done it capacitively. Actually, in one of the works, we were able to measure torsion by how many times we twisted something. Those were capacitive sensors. There's been some really amazing work on measuring tactile forces. So when you rub your finger across something, it's not just measuring pressure, but it's measuring vibrations. And the liquid metal wires are capable of measuring that with the right circuitry. There has been some work on sensors that can measure, what would you call that? Like tip and tilt, angular measurements.
Mm-hmm.
So by taking little beads of liquid metal and having them, when you tilt this way, the liquid metal goes down, and if you tilt the thing this way, the liquid metal moves. So that's also another thing that's been measured. People have used it for antennas, which is not really a sensor, but it's a electronic device that can measure RF radiation. People have also used it for making inductors, and so that's another thing. So you could sense magnetic fields using the coils. People have used it to measure temperature because resistance changes with temperature. You could probably use it for measuring pH in an electrochemical environment. So yeah, touch, vibrations. I don't know. That's off the top of my head. Those are the things that come to mind. I would say by itself, it's not a great sensor just because it's so conductive. But with some modifications, like some of the stuff I showed today, you can measure capacitance and you can measure, changes in strain or compression very, very sensitively.
Okay, thanks. There is one more question from Luis Alberto Jimenez. Luis Alberto de León.
Yeah, good morning.
Hi, good morning.
I have a very simple doubt about the equipment you're using for the 3D printing.
Yep.
Yeah, like what equipment are you using for the printing? Is it like 3D printer or something?
Mm-hmm.
Like the
Yeah,
normal?
so sorry, go ahead.
No, sorry.
Oh, okay. So this video, I'm actually very proud of this video because this was actually done by an undergrad that worked in my lab. So I know there's many undergraduate students that are on this call, and this student was in my class, and I realized he was very talented, and I kind of just like set him free in the lab, and he came and he brought me this video, and I almost fell out of my chair because I asked another student to do it, and the graduate student couldn't do it. And so the undergrad got this to work, and I said, "How did you do this? Like, we don't have a 3D printer in our lab." And he said, oh, I built it using spare parts from my trunk from his car. So the very first version of this printer was a nozzle, a needle. And I think he attached it to either a pressure source or a syringe pump, and then he kind of manually moved it all over the place. So now we have a little bit more fancy version. So now we have a syringe. So it holds a nozzle like this that has liquid metal, and then there's a pressure controller on the top that controls the pressure. Mm-hmm. And then we can move that with respect to the stage. So we have what's called an XYZ stage, which can control the X, the Y, and the Z. But your question actually underscores something that I think is important, which is if you look at this second video. So when I look at this video, to me, what it looks like is we're pushing the liquid metal out, like, somehow like with a pump, and we're coordinating the movement so that it prints. The reality is all we're doing is applying a little bit of pressure, and not enough pressure to make the metal come out. The metal only comes out due to the shear between the metal and the substrate. So let me give you an analogy. In this pen that I have, actually you can see there's ink in here, right? And the ink is this tall, which means there's a gravitational force on the ink, but yet the ink doesn't come out. I can hold it here and it's not going to drip. It's only when I bring this in contact and shear it across my hand that I would actually get the ink to come out. And that's actually what we do here. So we're not changing the pressure, it's constant. And so we bring it down, and as soon as it comes and touches the surface, it's basically like pulling the liquid metal out. So on the one hand, this is really good because we don't have to coordinate a pump with the movement of the needle. But it's bad because it means you have to control the distance between the needle and the surface. And so that part is a little bit tricky. And so for that, we've just gotten a stage that we can control the height. And so that way, when you go across, it stays flat. So I don't know, hopefully I answered your question, but it's at the heart of it, it's quite simple. It's just a needle with some pressure and it moves. So.
Yeah, you did. Thanks.
Oh, great. Thank you.
Okay, Michael, there are some other questions.
Okay.
I have to maybe formulate just the last one and send you the questions to your email so you can
sure. I'd be happy to answer any more questions. Sure. I love questions, so thank you so much.
Okay, the last question of this season is from Marco Jaramillo, and he's asking about how well those liquid metals hold their properties under constant stress and temperature changes.
Well, let me go back to this printing video, just to maybe be a little bit funny. So in this video, if you remember, we took droplets and we stacked them. So these droplets are it's like building a snowman. You just stack these things up. And I wanted to show this because the reality is if you like hit the table that these things are resting on, they'll fall over. So by itself, they're not very stable because remember, it's only a few nanometer oxide that holds that shape. So for a practical application, you really need to put this inside of rubber or something like that. And so for that, like this video I showed, like this one, where we made these stretchy wires. These ones are very stable. Oops. Okay. These ones are very stable. So we've done measurements where we've taken them and we've stretched them, I don't remember, at least 100,000 times. and it's very consistent. The way the resistance changes with strain. We haven't done a lot of thermal cycling, but I believe it should not be a problem. The bigger issues to me, since sort of the spirit of the question is like practical, like could you actually make these wires? So some of the questions are, number one, how do you make contacts to the liquid metal? Because somehow you've got to touch it to something else. And what most people have done is to use copper, because that seems to be pretty stable, or stainless steel. Those seem to be pretty stable in the presence of the liquid metal. Another issue, in my opinion, or something that I was nervous about, is like, what if a child gets this and they decide they want to like pull as hard as they can and they can break it, or they take a bite and the liquid metal comes out? Well, it's not toxic, but it's because it's a liquid, it's just easier to get it like on your skin and your mouth. So I worry a little bit about that. Another issue is gallium is expensive. It's about $1 a gram. So unless you really need the stretchability, it doesn't make sense to use it. And then there's one last thing, which I think talk about on Wednesday, which is in water, if you expose it to water, it actually, that passivating oxide doesn't work very well anymore. It actually starts to become unstable. So those are some of the issues, cost, effects of water. And so, if you put it in like a fabric that would be washed, I would be concerned long-term. But there's actually a company that's trying to commercialize this now, and there's some companies that are trying to use some of this stuff. So I don't know that we'll ever see it in commercial products, but we might. I don't know. It's hard to say.
Okay, there are some other questions, but we are running on time.
Okay.
So
I was worried that it was just going to be a lot of people staring at me, but I'm glad there was questions.
No, there is some here. For example, there is. Okay, I will send it to you.
Sure.
And maybe you can address this in the next session on Monday, if you agree.
Yep, be happy to.
Okay, many thanks, Michael, for your nice presentation. There are a lot of thanks and congratulations in YouTube and also here in the chat. And we are just waiting for Wednesday to solve some other questions and know a little bit more about liquid metals. I just have to give one final note. The Zoom platform will remain open if you want to stay here for the next session of Dr. Sandra Rodil. And for those who are following on YouTube, this session will be closed and will start at 11:30. So thanks for your attention and see you. Michael, see you on Wednesday, and all others see you in a while.
Thank you all.